Thanks for the introduction. Yeah, so in this session, I will present our work on provably secure anonymous attestation with TPM 2.0, which is a joint work with Jan Kamenisch, Likon Chen, Anja Lehmann, Dave Novik, and Rainer Urian. So let's get started. If you buy a laptop nowadays, then chances are that it comes with a TPM embedded in it, a trusted platform module. This is a secure cryptographic chip that can handle cryptographic keys and so create keys, store them in a secure manner, and use them in a secure manner. And what it can also do is it can measure the state of the host system, so the laptop in which it's embedded. And that allows it, for example, to verify the boot sequence of a laptop. So when it's booting, at every time the next software is loaded, the TPM can measure which software is being loaded there and end up with one digest of the boot sequence that's being executed. And now it might be interesting to perform remote attestations of this. So to convince a remote verifier that certain good software is being loaded. For example, you could think of a corporate network where every laptop must first convince the network that they're not running malware before they're allowed onto the network. So this process we call remote attestation, and usually that's a two-phase process. In the first step of this process, the platform, so the laptop with TPM, talks to a so-called issuer. This is some authority, usually it's the manufacturer of the TPM, that has to do some registration step. It has to issue some credential. This is a one-time activity, and then the platform can sign such attestations. So it can give some cryptographic proof to this verifier that certain software is loaded, and this laptop might be in a good state. Now, we could do this with standard X509 certificates that we've seen in the past days, but then your privacy might be at risk. If you do these attestations to many different verifiers, then every time the verifier sees which TPM is being used, which might harm your privacy. So what we want to do instead is direct anonymous attestation. Now we do the same thing, but the signature that goes to the verifier is anonymous, meaning that the verifier will believe that the signature comes from some secure TPM, but doesn't know which one. And so we have some security properties for DAA, and informally that means unforgeability. So no one should come up with a signature on some message, even though no TPM ever signed that message. And of course, in this scenario, we don't trust the host computer, right? So we don't want this corrupt host laptop to come up with an attestation that it's actually in a good state. And second, we want to have anonymity. That was the whole point of anonymous attestation. And we want that to hold even if this issuer, this authority is corrupt. So no attestation that the platform makes should leak any information about the identity of the platform. We have some more properties, but I won't go into detail on those. So in terms of history, this was introduced in 2004 by Brickel, Kamenisch, and Chen at CCS, and this was designed for the TPM 1.2 version. This used RSA keys, and as you know, RSA needs large keys to be secure. So when the 2.0 version of TPM came around, they switched to the elliptic curve setting, in particular with bilinear pairings. And they also reworked a little bit how the TPM supported anonymous attestation, and they did it in a nice way. What they did is make the TPM part of the protocol so generic that it allows for multiple different DAA protocols to be supported. Now, all of this is also standardized by ISO, and there's hundreds of millions of these TPMs being sold. So this is pretty widespread. And also, more recently, there's new interest in this. For example, by the FIDO Alliance, they're trying to standardize passwordless authentication. They're looking into using these anonymous attestations to convince somebody that a key is indeed securely stored inside the TPM. And Intel SGX is using anonymous attestation as their mechanism for remote attestation. They call it EPID, but it's the same thing. Now, there's many different DAA protocols, but they all work roughly in the same way. And that's what I'm going to show you here. So as I said, it's a two-step process usually. So first we have this registration phase that we need to execute once. And in that phase, the TPM chooses a secret key that it will keep secure in its own memory. And then it will talk to this issuer, this authority, and convince the authority that this is a true TPM, and then the issuer will place a blind signature on the TPM secret key. This is what we call the credential. Now, when that is done, the platform can start doing these anonymous attestations. And that works with the so-called zero-knowledge proof. And what that does, it convinces the verifier that some message M, which is the attestation message, so whatever the TPM measured, that some message M is signed by some key that was certified by the issuer. And now this is a zero-knowledge proof, so the verifier will not see the secret key of the TPM or the credential, so it will not learn which TPM it was, but it will still be convinced that this is some legitimate TPM because it trusts that the issuer only issues these credentials to valid TPMs. Now the difference between the different DEA protocols is in the type of membership credential that they issue and in how you instantiate the zero-knowledge proof, which are the attestations. So for the TPM 2.0, we are in this elliptic curve setting, and there are many, many different protocols for anonymous attestation, and you can sort of see them as two lines of work. So the first one is based on the so-called LRSW assumption, which is some cryptographic assumption that we have. And the second line of work uses the strong Diffie-Hellman assumption. And now the good thing is that, as I said before, this TPM2 can support protocols in both these lines of work, which means that if now it turns out that one of these two assumptions does not hold or is insecure, then you don't have to throw away all your TPMs. We can still use the other line of work. Unfortunately, previous work showed that almost all security proofs in these schemes are actually flawed and do not prove the security. Some of them are actually forgeable, others we're not sure, but there's no proof that this is secure. Now there are two schemes that have security proofs that seem valid, but they are actually also problematic. They are sort of incompatible with the current TPM. Because the TPM is a very lightweight chip that only has a handful of commands, and it's very hard to keep state between commands. And it would be very difficult to implement those two schemes on something like this TPM2 is. So we have a problem. We have this. We want to do anonymous attestation, but there's no provably secure scheme that can do that with something like the TPM 2.0. So that's our goal of today. Now let's look at this TPM2 and how that actually works. So I told you that attestations have the form of a zero-knowledge proof, proving that you signed some message. Now here on the right-hand side of this slide, you see the simplest zero-knowledge proof, which is called the Schnorr proof. And here, the prover proves that he signed some message M with a secret key that he does not reveal. For a practical DEA scheme, the host would need to extend this proof to also prove this part that this secret key is certified, but for simplicity, we look at this now. So you see that this protocol roughly has 3 steps, and we have 4 commands on the left. So on the left shows the relevant TPM commands useful for anonymous attestation. The first one creates the key pair that you use, and the rest corresponds exactly to the steps of this zero-knowledge proof. Now this looks very good, and we know that the zero-knowledge proof does not leak information about the key that is being used, so we might be convinced that the TPM protects its key properly, but there is actually a problem there. And the problem is the so-called static Diffie-Hellman oracle. What that means is that the host, and remember, we don't trust the host in this scenario, we want the TPM to verify that it's in a good state. The host can actually learn a lot of information about the secret key with these 4 commands. And what it can do is it can give any point on a curve, let's say P, and it can get back P raised to the secret key of the TPM. And it can repeat that process to get then P raised to secret key squared and cubed and so forth. And it turns out that with such a sequence of numbers, it becomes much, much easier to break the discrete log problem. Actually, in fact, on the curves that they use in this setting, which are Barrett-Neric curves, the security could drop to a very uncomfortable 85 bits. So we should remove this, this static Diffie-Hellman oracle. And now we're not the first ones to notice this. This has been noticed by Xie et al. In 2014. And they have some proposed fix for this. They notice that we shouldn't be able to call this commit command on every point P, but only on certain points with certain structure. And what they propose is to add a new command that proves to the TPM that this point is of good, it has this desired structure, and then the TPM should remember that, and then later we are allowed to use those points to compute these values later. Now this does solve the problem, but we're still not entirely happy with this, because there are three problems. First, we're adding a new command, which is an inefficient command because the TPM must verify a zero-knowledge proof. Second, it needs to keep state to the next command to remember that this point was a good point. And finally, this is all specific only for one of the types of DEA schemes. So it does not support the other scheme. So we want to do better than this. And what we came up with is a different approach. We don't specify the point that we want to use, but we specify a string that we hash to a point. Now, this seems like a small difference, but this actually removes this oracle altogether. But of course, we changed the interfaces. So now we need to think about whether what we have is still useful. And so we looked at these protocols, and they needed some work and some changing, but actually we can make them work with these commands. For that, I referred to the paper. So now we're wondering whether we're done. Did we achieve our goals yet? And remember, we need two properties, enforceability and anonymity. So do we have those now? Turns out we don't. When these interfaces were announced, there was a proof that they would guarantee this enforceability that we want to have. But again, unfortunately, there's a flaw in the proof, and this enforceability cannot be proven and might in fact not hold. There is a proposed solution by adding a nonce, which would fix our problems again. But now we weaken our anonymity. Before, we did not rely on the TPM for anonymity, and now we actually do. So we have the enforceability that we wanted, but now the anonymity went down. Okay, so we were thinking about this again, and the solution could be to have a jointly random nonce that you compute. So the host adds to the generation of the nonce, such that our anonymity is also preserved while also having enforceability. So now on the left, you see 4 commands, the same 4 commands that we have in the current TPM spec with minor changes in 2 commands, and we think this is actually a useful interface. So we went on to see what we can do with this interface. And what we can show is that there's a wide class of zero-knowledge proofs that we can create with this TPM. So the host can extend this proof that the TPM does, and we prove that all these equations are anonymous and enforceable with some TPM contribution. And now this is very useful, because from this we can very easily prove that we can make provably secure DAA schemes, so both under the LRSW and the strong Diffie-Hellman assumption. And actually, because it's so generic, we can do even more than that. So we looked at other protocols where you have a key that you want to keep secure and where that you need to use to make zero-knowledge proofs. And eCash is an example of that. So in eCash, you have a wallet of digital money protected by some secret key. And of course, you want to keep that secret key secure. Now, what this result allows you to do is place that key inside the TPM, and from this generic equation that we show we can compute, we can directly show that this is secure and that we now harden the security of eCash. For uProof, which is Microsoft's attribute-based credential scheme, we can do the exact same thing. So we can make it more secure by placing the secret key inside a TPM. And we also think that this might benefit future DAA schemes. So as I said, the variations are typically which credential scheme you use, and if there's a new signature that's more efficient, it might still match this equation, and then it'll be very easy to prove that you're secure with a TPM2. So in conclusion, we showed that we can do provably secure anonymous attestation, both under the LRSW assumption and the strong Diffie-Hellman assumption, with minimal changes to the TPM 2.0. So we added no new commands. We only did small modifications in 2 commands. And of course, we went to the TCG, the body that standardizes TPM, to show them these results. They've already accepted some of our proposed changes, and others are under review. And of course, we hope that they will all be accepted eventually. And one result that we think is interesting is these class of zero knowledge proofs that we can then prove with this TPM. We think that could be useful for other protocols as well. And finally, we saw that many of these standardized schemes in ISO and other places are actually not provably secure, and we think that that is a takeaway message that we should improve there and focus more on provable security from the beginning, and especially before standardization. And so this is also where we will continue in trying to improve these standardized schemes to actually have provable security. Thanks for your attention, and I'd be happy to answer questions.
David Smith, Ripple. Hi, thank you. That was great. Have any of the changes required for this to be used from Trousers or TCSP been submitted?
So I didn't understand the question.
The open source software stack for using the TPM, Trousers and TPM tools?
Oh, right. Well, I think they follow the official specification, right? So before it's all in there, I don't think we'll see it in open source implementations. But I mean, it would be nice to do that. And we're thinking about first doing a prototype in that, and then coming back to the TCG.
Can I play with it now?
Okay. Thanks.
So I have a question regarding revocation mechanisms and what to do about them. So does the TPM2 specify some mechanism for revocation? And would your model extend to it nicely, or is it much more complicated? What's the outlook for that?
So they don't specify, so all that the TPM specifies is these 4 commands that I showed. Now the bigger schemes, they come with revocation capabilities. So one is this verifier local revocation, which means that if some secret key of a TPM leaks, then we can detect that and we can ban that key. And we have signature-based revocation, where if there is a signature that we know is bad, then we can put that on the signature revocation list, and then every next signature should prove that he's not on that banned list. So those 2 mechanisms are there.
I see, but so they are built on top of the 4 commands in a black box manner. There is no extra mechanism.
Right. Yes. Yeah.
And then maybe one curiosity question. Do you know what fraction of the TPM2s actually support DA or use DA on a regular basis?
That's a good question. I unfortunately don't know that, but yeah, that's very interesting. I would like to find that out.
Okay, well, thanks.